Hello everyone. So in the previous videos we saw Fibonacci numbers, sieve, binary exponentiation, and in this video we will start Euler Totient function. So Euler Totient function is defined for a number and it is represented by phi of n. And what this return, what is the value of phi of n? Is basically number of integer x between 1 and n whose GCD with n equals to 1, means which is co-prime to n. Now what is phi of 1? 1 basically only number 1 is co-prime with 1. Phi of 2 is 1. Phi of 5 is 4 because 1, 2, 3 and 4 these numbers have GCD 1 with 5. Phi of 6 is basically uh, 1, 2, 3, 4, no 4, 3. So number 1 and then 2 is having GCD 2, 3, 4, 5, GCD of 5 and 6 is 1. So phi of 6 is 2. So let's see this one. So phi of 1 is 1, 2 is 1, 6 is 2, 7 is 6. Now let's see some property of phi. Tell me what is the phi of a prime number p. So you know that prime number is divisible by only 1 and itself. So first of all the numbers between 1 and p, 2, 3 up to p minus 1. When you take GCD with this, there is no common divisor, so it will give 1. And also GCD of 1 comma p is 1. So how many numbers are there having GCD 1 with p minus 1, right? So phi of a prime number is prime number minus 1. Now tell me what is the phi of p raised to power k, where p is prime number. Now a prime number raised to power k is divisible by p, 2p, 2p square, something like that. So number of all the numbers which is divisible by p is divisible by have GCD not equals to 1 with p raised to power k, right? So how many numbers are there? P raised to power k minus 1 numbers are there whose GCD with p raised to power k is not equals to 1 because there is a common divisor p. So phi of p raised to power k is basically total number is p raised to power k. Out of this, you remove p of k minus 1. So phi of p raised to power k is this, right? Next property is phi of a into b. Phi of a into b is where a and b are prime to each other, means GCD of a comma b is 0. Is basically phi of a into phi of b. You can derive it as similar to this one. There is a more general version of this when this is when a and b are not co-prime, but we don't use that too much. So let's see. Now you have to remember these properties; these are very useful. Now, how to find phi of n efficiently? First, you can simply run a loop from 1 to n and you check which number have GCD 1 and you add 1 to the count. Fast way to do this is basically find prime factorization of n. Let's suppose prime factorization is p1 raised to power q1 into p2 raised to power q2, right? Now you have seen that phi of a and into b is phi of a into phi of b. So if you take phi, these are all co-prime to each other, so you can separate it. So this is basically equals to phi of p1 raised to power q1 into phi of p2 raised to power q2 and so on. Now what is phi of p1 raised to power q1? We have already seen this. So this will be p1 raised to power q1. First of all, you can rewrite this as, you can take p raised to power k common and you will get 1 minus 1 by p. Right? So this will be p raised to power q1 you will take common and 1 minus 1 by p1. Similarly, p2 raised to power q2 into 1 minus 1 upon p2 and so on. Right? Now take out all these, combine all this. P1 raised to power q1 into p2 raised to power q2 into p3 raised to power q3 and so on. And these here 1 minus 1 upon p1, 1 minus 1 upon p2. Now you see that this number is basically n, prime factorization of n. So you can write n into, write this 1 minus 1 upon p1 into 1 minus 1 upon p2 into 1 minus 1 upon p3 and so on. So phi of n is number multiplied by 1 minus 1 upon prime, all the prime multiplication. Right? So you get this. So let's see the code, how to write this. So first find the prime factorization of, or you can do prime factorization at the same time when you are and you can calculate phi at that time only. So let's see how to calculate phi for a integer n. So you initialize the result with n and you go from 2 to root n, and if there is a number which divides I, then you will divide it until it becomes until it becomes divisible. Means it is a basic prime, how to find the prime factorization. This is a in root n complexity. So after that you do result minus equals to result by I, because the I is the prime number which divides n, right? So result minus equals to result by I, and if n is greater than 1, it means n is itself a prime number, and for prime number, just prime number minus equals to p by n. Now why I am doing this, you can take n inside, so n minus n upon p1. Result is initially n and you are subtracting n minus n upon p1. Now what you will get, this you just multiply with this. So let's represent it with x. So you will get x minus x by p1. That's why we are doing result minus equals to result by I. I mean result equals to, or result minus equals to result by I. This is basically result multiplied by 1 minus 1 upon I. We can't calculate this because this is not an integer, so we have to do this. So result minus equals to result by I, and if it is a prime number, then simply result minus equals to result by n, and we return the result. So here see phi of 10 is 4, right? So you understand this, like I am iterating from 2 to root n, and if a number divides I, so I is the prime number p1, so I am updating the result, and also I am removing all the power of I from n, so that it won't be divisible again by some co-prime number which is a multiple of I, right? Now this is basically useful when you have to find 5 for a single integer. But what if I tell you to find 5 from 1 to n? So in this, you can use the concept of sieve basically. So initialize 1 to n with I, means the same number 1, 2, 3, 4, 5, 6, and here see that I initialize 5 with I, and now for all the prime numbers, 2 is a prime number, so I will iterate on the multiple of 2, and I will do result minus equals to result by prime, means phi of I minus equals to phi of I by current prime number p. Right, so if I am 2, I will subtract, uh, I go to multiple of 2, that is 4, 6, and I will do 4 minus equals to 4 by 2. So it will become 2, it will become 6 minus 6 by 2, 3. And when I reach 3, I will go to multiple of 3. So I will reach 6. So 3 minus equals to 3 by 3, that is 2. So see, 5 of 6 is 2, 5 of 4 is 2. So here I take from 2 to n, and if that is a prime number, if phi of I equals to I, then you do go to multiple of I and then do phi of j minus equals to phi of j by I, right? And you also do for this 2 minus equals to 2 by 2, that is 1. For all prime number, its phi is p minus 1. That's why I have to include I also here, right? Now, how is this working? Because let's see, I am at index I. Then what happened? I This number is changed by all the prime numbers before it, which divides I, right? So let's suppose P1, P2, P3 divides I. So every time what I am doing, I minus I divided by P1, right? Take I common. So I into 1 minus 1 upon P1. And then when I reach P2, then again I am doing it, this number minus equals to this number divided by P2. Then so when you take common, you will get 1 minus 1 upon P2, right? So this boils down to the same formula. That's why I am doing this. So this is the function for phi 1 to n, and when you calculate this, you will get this phi of 1 is 1 to 1, right? So in the next video, we will see some application on totient function, and if you have any doubt, you can comment. Thank you.